Hello, I'm François Lénon, PhD student at Lisbon Laboratory at Armeti Institute of Technology, and I'm glad to present you our work on building a cognitive architecture for intuitive and iterative task learning in industrial collaborative robotics. So let's start with some context. In recent years, classical industrial robots have left their cages to become more collaborative thanks to better sensors and higher-level programming libraries. Nevertheless, their behavior still remains far from the natural interaction between two human coworkers. In that context, we aim at building a smart robotic assistant. As an assistant robot, it should be able to have natural and intuitive interaction means with the human coworkers. It should be able to learn in a teacher-learner setting, where the teacher is the human and the learner is the robot. And this assistant robot should be able to adapt to each individual preferences. For instance, if someone is right-handed or left-handed, the robot should be able to adapt its behavior to this fact and give an object to the main hand of the human. As a smart robot, we want it to be rational, it will have trustful decisions, it should be able to react to unpredictable events, and it should have learning abilities such that it could adapt to a broad set of tasks. Such a smart robotic assistant could be really helpful as non-programmer experts could adapt and reconfigure robots specifically to their needs without programming and knowledge in robotic. To fulfill these specifications in a manageable and understandable way, we need a robotic cognitive architecture. So what is a robotic cognitive architecture? We can have two views on them. One in terms of control layers and one in terms of representations. In terms of controls, we have a physical and social world. At the lowest level, the robot is able to perceive this world and to act in it. It has a long-term goal at the deliberative layers that it is able to translate in terms of task sequencing as the executive layer. In terms of representations, here again we have the environment and the humans that the robots has to learn to represent in terms of a world models through memories and different inner processes such as learning and decision making. When we have this architecture, we can build an interactive task learner. There exists some ITL in the literatures, but they often focus on the highest level of cognition. Perceptions and directive abilities are still limited, and to our knowledge, there is no adaptation yet to industrial use cases. So in that context, we decided to propose our own architecture, and the first prototype was implemented in Python 3 in order to ease the implementation and the integration of deep learning modules. So we want the knowledge to be modular and actions to be as modular and reactive as possible. So we build them around knowledge graph and behavior trees. In order to have interactions that are natural and multimodal, we exploit vision, speech, and gesture demonstrations. We learned the perceptual symbols in a world that is noisy and dynamic, so we exploit deep learning techniques and deep learning modules. And of course, we want to validate this architecture on industrial use cases. Here you can see a high-level overview of this architecture. So we have an environment with an instructor and the working space. The ITL agent is able to perceive the humans, to perceive the environmental space, and to perceive itself, so with proprioceptive perception. It is able to build a world model, so with working, episodic, and semantic memories that are relational graphs, and a specific action memory, so the procedural memory, based on behavior trees. Of course, the ITL agents have also some prior knowledge that it has to leverage in order to learn new procedural or new perceptual information by interacting and dialoguing with the instructor. To illustrate that, here is an example. So imagine an operator that asks the robot, give screwdriver. The robot does not know the concept of the action give, and it does not know what a screwdriver is. It has some prior knowledge. It knows that what pick up object means, what put in hand object means. It has some world model. It knows that a general object has some perceptual and grasping affordance features. So the grasping affordance is where to grasp the object. It knows that a general object can be located on the working space. And we have also human and communication models. It knows that a general human has a hand that can be located, and there is a goal-driven communication protocol. So here is a representation of the working memory of the agent. So the operator asks the robot, give screwdriver. The robot does not know the word give. but it is able to locate that there is an unknown object on the working space. It's able to recognize the operator François, that it has a right hand, and it is able to locate it. So the agent asks, I don't know the action give, what is the goal of the task to give? The operator responds that the goal is screwdriver in hand. So here again, the robot analyzes the utterance. It sees that it doesn't know the word screwdriver, but the hand is known, and it is the right hand of the operator. So it asks, I don't know the name screwdriver, please show me. You can see that the operator moves its right hand above the previously unknown object, so the screwdriver. And thanks to that, the robot can now learn the perceptual features of the screwdriver. So here this node is linked to classical convolutional neural network models that help in learning these perceptual features. So the agent says, I learned the screwdriver. Everything is graded in this utterance. The agent learned the goal of the give action, so in screwdriver hand, and it asks for the procedural part of the give action. So it asks, what is the next subtask of to give? In order to do that, we represent actions in terms of behavior trees. So for instance, we can say that the give action is the sequence of tasks. It's the sequence of the primitive action pickup and of the primitive action put in hand. Here, actions are represented in terms of preconditions and postconditions. So here you have the behavior trees for the pickup action and the behavior trees for the put in hand action. For instance, for the pickup actions, in terms of preconditions, the robot has to locate the object. So this is the case for the screwdriver, but the robot does not know how to grasp the screwdriver. So when the operator says that the first subtask of to give it's pick up screwdriver, the robot agent sees that it does not know the affordance of the object. So it asks, I don't know the grasping affordance for screwdriver, and please show me. In order to do that, we exploit learning by demonstration modules that we have developed. So we show to the robot where to grasp the object. A conventional neural network model learns this location and is now able to predict the grasping location. So the agent learns the grasping affordance for the action give screwdriver. Everything is grounded. The robot can carry out the task pick up screwdriver, and the operator now has to tell the robot the second subtask. So the second subtask is to put in hand the screwdriver. So here the robot has all the knowledge to carry out this task. It places the screwdriver in the hand of the operator. It sees that that fact matches the goal of the task to give. So it says, I perceive the goal in screwdriver hand and can learn the action give. The agent is able to generalize to any type of object. So if the operator now asks the robot give range, if the robot knows what a range is and how to grasp the range, it will be able to give the range without relearning everything. Another type of issue that we could have, for example, is to store back the screwdriver. In order to do that, we have to keep track of the relevant properties across time. So here the location of the object. And in order to do that, we exploit an episodic memory. So this is a replay buffer of linked episode of the working memory. So that we store across time. So I will now show you a video example of this give screwdriver learning task. So here you can't hear the operator, but it talks to the robot. In order to do that, we exploit the Google Speech platform and to do the speech to text procedure, and then we analyze the utterance for the understanding and learning part. We implemented that on a UR10E universal robot with a wrist-mounted IGBT camera. The depth channel of the camera helps us for segmentation and background removal of the working space, and the RGB channels are used with the OpenPose deep learning framework in order to do the hand tracking. This hand tracking helps us then to show the robot where is the screwdriver and where to grasp it. So overall, you can see that step by step, interactively and in an online fashion. The operator is able to teach the robot um, the perceptual and the procedural parts of the gift screwdriver task. Overall, all computation is done on a regular gaming laptop, so a mobile Alienware 15R3 with an NVIDIA 1070 mobile GPU. Yeah, so you can see, yes, that the robot has now learned the gift screwdriver task. So to conclude, at current state we have some interesting results, but there is room for perspectives and potential improvements. So in upcoming works, we plan to bring uncertainty management to our system. And uncertainty metrics will help for decision making, sentient fusion, and disambiguation. We also plan to bring multiple user interactions, so how the robot can learn from different users. And in this upcoming work, we'll focus on adaptation to preferences, and we validate that on a multi-user setting. In terms of long-term improvements, we plan to improve the overall dialogue protocol. We could also add more sensing capabilities such as turkey and force sensing. We'll have to bring more learning paradigm, and overall, we want to assess the ease of use of our architecture. So we'll have to validate that with non-programmer experts in a real-world setting. So here are some publications related to this work, and thank you for your attention.